Good morning, everyone. Welcome to the security seminar here at Purdue University. Today's speaker is Professor Wenke from the College of Computing, Georgia Institute of Technology. Professor Lee's research interests include network security, intrusion detection in particular, and network management, distributed data mining, database systems, and workflow modeling and management. Today, Professor Lee will talk about architectural considerations for anomaly detection.
Thank you, Lin-Hui. Apologize for delay. So I think security is less a problem than usability. So if anybody can solve this problem, I think we are much better off. So, so I guess the audience here are very familiar with defense in depth and in general security. So I'm going to just fly through the slide here. Essentially, I use this slide to tell people that hey, intrusion detection is important. So, but you all know that. So I'm going to skip that. So today I'm not going to talk about any new algorithms. I'm going to actually talk about once you have the anomaly detection algorithms, that you have the individual modules, how to put them back together to have a system that you have hopefully a lower false positive rate. So I'm going to talk about, in particular, two architectural styles. One is what I call Cascade. Another is essentially correlating a bunch of sensors. And I'll give you some examples. So again, I think this can be skipped, and including misuse and anomaly. So, all right. So, so the talk starts here. So again, this is somewhat familiar to you guys, I'm sure. And so, what are the sort of key performance metrics if you want to sort of evaluate how good an IDS is doing? So obviously, the most intuitive and most often used is the detection rate, right? And then some people like to use false negative rate, and also false alarm rate is also important, right? You can't ignore false alarm rate because if the idea is giving you a lot of false alarms, then people will stop using it. And then the third one there, Bayesian detection rate is also very important, but tend to be overlooked. Right? So that's a metric that I want to explain more. So how do I remove this? I'm attempting to do this. Hopefully it's not going to break. But you never know. So good. All right. So so the Bayesian detection rate tells you that if an IDS tells you that there's a so if IDS produce a alert, right? So if you're a user of the IDS, suppose you're a sysadmin, or you're writing some software that would sort of try to do automatic response. So then you want to see that when IDS produce a alert, what's the probability that there's actual real intrusion going on, right? So that's what the Bayesian detection rate would tell you. So I mean, you can express it using the Bayesian theorem. So one observation here is that, and of course, if the false alarm rate is 0, and then the Bayesian detection rate would be very good. But on the other hand, we know that in IDS, the typically in algorithm we have some false positive rate, and so then you have this sort of phenomenon called the base rate fallacy. So essentially, typically what we call the base rate here, meaning the prior probability that you have some intrusion in the data that you are analyzing. Let's say in traffic data or your OS audit data. This probability that you will see some intrusion there actually is very low. You say that's not true because we hear that intrusions are happening all the time. I'm talking about with respect to the total amount of data that you are analyzing. Suppose you're looking at the network traffic, right? So in a day, you will see probably millions or tens of millions of packets. How many of those packets are actually associated with some intrusion? Very, very few, right? Maybe a couple thousand, right? So this rate is very, very low. So if you plug in these parameters to the formula, the point is that even if your perfect detection rate, even if the false alarm rate is very low. So here, in numerical example is that you have a perfect detection rate, and the false alarm rate is low enough, right? But then the base rate is also very low, and this is not. This is quite real, right? In a normal daily traffic, and then the Bayesian detection rate is only 66%, meaning 1/3 of time the alert from the IDS doesn't tell you anything, right? So it doesn't tell you there's an intrusion. So that's a problem. So so this is more from a usability point of view, right? So IDS produce some information, and then you think about how those information is being used for you to manage the system. So we can easily plot a few plots here to show that essentially, if the base rate is very low, then it doesn't matter how you improve the false positive. Suppose the base rate here is very, very low, so this blue line here. And then even if you improve the false positive, meaning the false positive rate is close to 0, your Bayesian detection rate is still very, very low. Okay, I mean you would want to have a higher base rate so that when you reduce the false positive rate, it actually matters. Okay, so the point is that if the base rate is so low, then it doesn't matter what you do. You can try all your best. Spend all your PhD years to work on a better algorithm. Okay, you say, hey, my false alarm rate is like 5% better. Doesn't matter. I mean, so that may not be fair to you, but that's actually the reality if you want to use the algorithm in the real world. So the implication to the IDS research and development essentially is that right now what we have is that we have too many false alarms in the busy network, and it's very typical to see thousands of false alarms every day. So there's a huge business out there called alert correlation, and a lot of companies, they provide the so-called managed security services to other companies, because these other companies, they just can't deal with all the outputs. Okay, so you can start business by, okay, I can look at your alarm data and tell you what are the real thing. So you think, well, wouldn't it be better if the IDS doesn't produce so much junk, right? So of course you can say you can always design a algorithm to reduce false alarms. Say if to 0, then then the Bayesian detection rate would be 1. But I think for all of you who know about IDS, that's a very difficult task. So this talk is about, okay, suppose we know about the limit about the algorithm and about the environment that the IDS has to operate on, meaning the base rate is very low. What can you do? Can you think about, from the architecture point of view, can you do something about this particular problem? So we think that in some cases, this is probably doable. But again, this is not like a complete work. So the first architectural style that you can consider is what we call the Cascade model. So in a Cascade, essentially you have the data at the bottom, and then the data will go through a stage, a series of analysis. So at each stage, the analysis module will throw out data. Okay, and then whatever is remaining will be passed to the next stage. So essentially, what's being thrown out would be quote unquote normal, or in this context may not be the pure sort of may not be the absolute normal sense in terms of security goal. It could just be that you're looking at a particular kind of intrusion or anomaly, and the data that you throw out had nothing to do with that kind of intrusion. Now it may have something to do with some other kind, but you don't care.